Hello, good morning, my dear students. This is again your Vinod Kumar, lecturer in Electrical and Electronics Engineering from the Institute of Government Polytechnic, Vadipalli. So the subject of AC machines with the semester of 4 and the subject code is 18EE403C. From the topic of single phase transformers, here is a subtopic of parallel operation of transformers. Parallel operation of transformers. What does it mean? Actually, if one transformer is not sufficient to drive the load, then some other transformer has to bear it. So when other transformer is bearing, so both the transformers should be connected in parallel to each other. Then only it can bear the extra load. So this is how the connections are to be made and how the operation is done to it, and what are the necessities, conditions, and all those things we'll be seeing in this session. In the previous class, we have learnt about the power transformer and distribution transformer and the differences between them and the Sampna's test. And I hope you have got all the points in these things. We have done a Sampna's test also with the connection diagrams and all those things with the explanation, and also we have done a problem in it, and I also given you some example problems in order to practice, and I hope you all have done with that. Now on the completion of this topic, you would be able to know the need of parallel operation of transformers, the conditions for paralleling of transformers, and load sharing between two transformers. Just please make a note of them. The need of parallel operation of transformers, the conditions for paralleling of transformers, and load sharing between two transformers. Please make a note of these 3 points. At the end, we'll be knowing all about these 3 topics. Please make a note of them. Okay, now we'll step into the topics. The parallel operation of single phase transformers. First, we'll see the necessity of it. First, we'll see the necessity of it. Parallel operation of single phase transformers are necessary for the following reasons. That is, continuity of service, efficiency, maintenance and repair, and future expansion. and future expansion. I'll erase it. Necessity is continuity of service, efficiency, maintenance and repair, and future expansion. Please make a note of these things. I'll just explain you each part. Continuity of service is like if two transformers are connected in parallel, if so, any of the transformer is failed to operate, then the other transformer continues to supply. So there won't be any interruption in the service. So that is the continuity of service. And when only a single transformer is bearing the load, it may cause huge heat, huge temperature, and the losses may increase. And when there are two transformers sharing the load, then the burden on the transformers reduces. That means the losses also reduces, and the further efficiency increases. And maintenance and repair. If any of the transformer is under maintenance or repair, the other transformer is continued to supply, and the repaired transformer can be maintained and repaired easily by disconnecting that. And the last, future expansion. Like if any loads are increasing continuously, since day by day the consumers are increasing, so and in order to meet the high demand, if there is another transformer connected in parallel, then that can satisfy to supply the load for the demand. So by this it can be for the future expansion. So these are the four necessities in order to operate parallel single phase transformers. Please make a note of them. Okay, moving on to the next. Advantages of parallel operation. So while operating the two transformers in parallel, what kind of advantages are achieved? Firstly, reliability of the system increases. Reliability. The reliability of the system increases. Cost of the standby unit reduces. Finally, the cost reduces. The reliability of the system increases. Cost of the standby unit reduces. Efficiency of the system increases. Future demand can be easily met. Future demand can be easily met with that. So please make a note of them. Reliability of the system increases. Cost of the standby unit reduces. Efficiency of the system increases, and future demand can be easily met. So these are the four advantages of parallel operation. Okay, moving on to the next. Conditions to be satisfied for parallel operation. What kind of conditions to be satisfied? The following conditions must be satisfied before connecting a transformer in parallel with the existing transformer. First, primary winding of the transformer should be suitable for the supply system voltage and frequency. The primary winding of the transformer should be suitable for the supply system voltage and frequency, and they must be connected properly with regard to their polarity, nothing but same polarity. These are some 2 points over here, and some more points are there in the next slide. The first condition is the primary winding of the transformer should be suitable for the supply system voltage and frequency, and they must be connected properly with regard to their polarity, nothing but same polarity. That means positive to positive and negative to negative. The other points are the transformer must have same voltage ratio, nothing but equal voltage ratio, and the other is X by R ratio, nothing but it is also called as percentage impedance of the transformer should be same. These are the four conditions should satisfy in order to connect the two transformers in parallel. Firstly, the voltage and frequency should be same, and next the polarity should be same, and next the same voltage regulation, ratio should be same, nothing but E2 by E1 should be same, and also X by R ratio should be same. Once again, we'll just analyze the points. First one is voltage and frequency should be same. Second one is polarity should be same, like plus and minus should be same. Third is the voltage ratio. Voltage ratio should be same. And fourth one is X by R ratio should be same. Simply you can note these 4 points. In a shortcut way. So these are the 4 conditions which has to meet in order to connect the two transformers in parallel. Next, conditions to satisfy for parallel operations. The equivalent leakage impedance in ohms is inverse proportional to the kVA rating. Same thing, this is the fifth point. This one is fifth point. Previously we have seen 4 points, and there is a last point over here. the equivalent leakage impedances like Z01 is equal in impedance to primary, like Z02 equivalent impedance referred to secondary. So the equivalent leakage impedances in ohms is inversely proportional to their kVA rating. That means the kVA is equals to proportional to 1 by either Z01 or Z02. The equivalent leakage impedances in ohms is inversely proportional to their kVA rating. This is not by, it's or. Or Z1, Z01 or Z02. Please make a note of that. If it is not here, I'll just make it again. Or Z02. Okay, then moving on to the, you can see here the parallel connection, circuit model for paralleling of two transformers. You can see the two transformers over here, transformer A, transformer A, transformer B. You can see here this is a positive polarity and this is a positive. The positive is connected to positive. I'll just show you the thing. Positive and negative. You can see this is a positive and this is a negative. This is again a positive to the second one and this is a negative. So the polarity should be same. That means positive should be connected to positive and negative to negative. Similarly over here, here he took this as positive and this as negative. Okay, see the positive polarity to positive terminal and negative to negative terminal. Here we didn't mention this is plus and this is minus. So this is plus and this is minus as I have indicated there. Now it's very easy to use. Plus to plus and minus to minus. See, plus to plus and minus to minus. Here he just given you plus and minus. So this is a connection diagram or a circuit model for paralleling of two transformers. So here there are circulating currents in between the turns. In a transformer A that is EA, and in transformer B it is EB, and the impedance is ZEA, and here it is ZEB. Please draw this circuit diagram. Okay. Load sharing by two transformers. Here you can see, consider two transformers running in parallel with same voltage ratios and impedance triangle. Consider two transformers. Consider two transformers running in parallel with same voltage ratios and impedance triangle. You can see this is a transformer 1, this is a transformer 2. And these are the primary bus bar for positive to positive and negative to negative. And this is the secondary bus bar. Since it is connected to the primary, so it is called primary bus bar. And it is connected to the secondary, so it is called secondary bus bar. Here it is an input, nothing but supply given, and here taken to the load. Just make the diagram. We'll continue. Now here you can see load shared by the two transformers. Here this is the first transformer EA, which is inducing EMF as EA, and the second transformer inducing EB. The negative to negative, positive to positive, the same polarity connected, so in parallel. And the first transformer EA is inducing the current of IA and has an equivalent impedance of A is R and X, that is ZEA. ZEA is equivalent impedance of transformer A. And there is a second transformer of EB, which is inducing a current of IB and has an impedance of ZEB, equivalent impedance of transformer B. This is a circuit model for paralleling of two transformers, and again these two are connected in parallel, inducing a common current of I and inducing a common voltage of V and sharing the common load of Z. Just make the diagrams parallelly. And in the second diagram you can see both EA and EB are same. Since in parallel the voltage will be same for any kind of sources, and both are inducing a common current of I, and that is splitting into IA and IB to the loads ZEA and ZEB, which are in parallel. ZEA is equivalent impedance of transformer A and ZEB is equivalent impedance of transformer B, and both are commonly sharing a common load of Z with a common current I and common voltage V. And here you can see the same diagrams again. We'll see some derivation part. Let EA is equals to no load secondary voltage of transformer A in volts. See here, EA is no load secondary voltage of transformer A in volts. Similarly, EB, this EB is no load secondary voltage of transformer B in volts. So these are EA and EB. So which are no load secondary voltages of transformer A and transformer B measured in volts. And we have ZA, that is equal to ZEA, which is over here, which is given as RA plus JXA. This is the resistance and this is the reactance, RA plus JXA. This is nothing but the equivalent impedance referred to secondary of transformer A measured in ohms. Are you getting or not? So ZA is equal to ZEA is equal to RA plus JXA, which is nothing but the equivalent impedance referred to secondary of transformer A measured in ohms. Similarly, ZB, which is over here, it is called ZEB, which is given RB plus JXB. This is R and this is X, which is nothing but the equivalent impedance referred to secondary of transformer B in ohms. Please make a note of all these things so that we can move on to the next slide. This is an important topic where this can be asked either in a theoretical or a description way, in a derivative way, or a problem can also be asked in it. So whereas the I is load current in amps, this is the I where it is over here, this is I load current in amps. Whereas V is load voltage in volts, load voltage in volts. And IA is secondary current of transformer A in amps, IA is over here, and IB is secondary current of transformer B in amps, IB is over here. and S is equals to total load to be shared by the transformer in kVA. S indicates the kVA power. We have the power equations we may have studied in electrical circuits like S, P and Q. S is for kVA, P is for kW and Q is for kVAR. Where S is apparent power, P is active power and Q is reactive power. There are three kinds of power. The transformer is always measured in kVA. That means apparent power denoted by S. So whereas S is total load to be shared by the transformer in kVA, and SA is load shared by transformer A in kVA, and SB is load shared by the transformer B in kVA. So whereas S is total load to be shared by the transformers in kVA, in that case SA and SB are load shared by the transformer A and B separately in kVA. The same diagrams under equal voltage ratios, under equal voltage ratios, EA is equals to EB. That means EA is equals to EB. Finally, IAZA, nothing but the impedance drops. IAZA is equals to IBZB, that is equals to total I into total Z is ZAB. IAZA is impedance drop. When the equal voltage ratios EA is equals to EB, the drops are also should be same. That is IAZA is equals to IBZB, that is equals to total drop also I into ZAB. This equation 1. Consider it as equation 1. ZAB is equals to ZA into ZB by ZA plus ZB. ZAB is nothing but when these two are in parallel, ZA ZB by ZA plus ZB. Consider this as equation 2. From equation 1, we know that IA is equals to I into ZAB by ZA. You can see here. Similarly, IB is equals to I into ZAB by ZB. That's the same for both. Now when we consider IA is equals to, if this is I into ZAB by ZA, that gets ZB by ZA plus ZB. IA is equals to I into ZB by ZA plus ZB. How this was formed, you can see here ZAB over here. ZAB is equal to ZA into ZB by ZA plus ZB. We just substitute this value over here. Then if this ZA and ZA gets cancelled, finally we will be left only ZB by ZA plus ZB. Finally, Ia is equals to I into ZB by ZA plus ZB. See here, since ZAB is equal to ZA into ZB by ZA plus ZB. If you just substitute this over here, you will be getting Ia is equal to I into ZB by ZA plus ZB. In the similar way, IB is equals to I into ZAB by ZB. From this case, Ia is equals to I into ZAB by ZA. So similarly, IB is equals to I into ZAB by ZB. Again, substituting the value of ZAB in this equation, you will be getting IB is equals to I into ZA by ZA plus ZB. So from that, V into Ia is equals to V into the Ia value is I into ZB by ZA plus ZB. Now the load shared by the transformer A, that is SA, that is equals to S into ZB by ZA plus ZB. And similarly, V into IB is equals to V into the value of IB is equals to over here I into ZA by ZA plus ZB. And then the same load shared by transformer B, that is SB, is equals to total S into ZA by ZA plus ZB. So these are the important formulas to be noted so as to make the problems. And please note down all the formulas. This is for SA, this is for SB. Make a note of that so as to do the problems. Okay. So finally, the load shared by the two transformers is also done, the derivation part. I should note all the equations and formula for that. So in this class, in this period, we have discussed about increased demand of the consumers necessitates paralleling of transformer. As I said in the previous, when the demand increases, the transformer should be connected in parallel of the consumer's necessities. The same polarity is the essential condition for paralleling. So in order to parallel, there should be the same. The transformers share the total load inversely as their equivalent impedance. Total load kVA is inversely to their equivalent impedances. The primary of the transformer must be suitable for simply voltage and frequency. Percentage impedance must be same. Load sharing of transformers. These are the things which we have seen. This is a simple summary. Now, are you ready for a small quiz? Please do it. The essential condition for paralleling of two single-phase transformers is that they should have the same. Guess the answer. The essential condition for paralleling of two single-phase transformers is that they should have the same polarity, rating, or current ratio, or percentage impedance. Essential condition. I think it's polarity. We'll just check it out. See polarity. This is the essential condition. The main condition. So this is the first question in the quiz. The second one is, if the impedance triangles of two transformers operating in parallel are not identical in rating, then the two transformers will. If the impedance triangles of two transformers operating in parallel are not identical, that means not same in rating, then the two transformers will get heated unequally, share the load unequally, run with different power factors, all the above. I think it's all the above, because if the two impedances are not same, get heated unequally, also share the load unequally, and runs with different power factors also. So it is all the above. There are some frequently asked questions like, what is the necessity of paralleling of transformers? State the advantages of paralleling of transformers. And derive the expression for load shared by each transformer. And state the condition necessarily required to operate the transformer in parallel with the existing transformer. So these are some frequently asked questions which you can expect in the examination. So that's it for today's class. Thank you one and all. We'll see you in the next class.